Good evening, good afternoon, whatever time it is. I recorded this twice and it hasn't saved correctly twice. Third time's a charm. Third time's a charm. That's what we're going. So it may be midnight. It may be the third time recording, but we got this. So today I am focusing on the formation of. Can this please go away? Why is this on? Why is it on? Okay, whatever. There we go. The formation of rare earth elements, specifically heavy earth metals, heavy precious metals, and even more specifically, siderophilic elements. Where do we start? Precious heavy metals have numerous applications, anywhere from jewelry to manufacturing applications, in your cars, in your phones, everywhere in between and on top and below. Looking at these heavy metals, we can look more closely and we can categorize them more specifically as siderophilic elements. These are elements that relate heavily back to the early periods of formation in our solar system. They are very common in these elements possess many building blocks that come from pre-planetary objects in our solar system, and the subsequent conglomeration of these subplanetary pre-planetary objects into planets leads to the what we know as today as the distribution of siderophilic elements in Earth's upper crust and upper mantle. And that's where my focus is kind of on today. And we're going to be looking even more specifically at the platinum group element, um, platinum group, whatever group of elements, platinum group elements. So, firstly, let's figure out what siderophilic elements are. Siderophilic elements, there are, I think, 18 elements in total. Um, the platinum group elements are just a subfamily of the pseudophilic elements that contain 6 elements, anywhere from platinum, palladium, rhodium, ruthenium, iridium, and osmium. Um, so we can, from studies, we can likely link the formation of pseudophilic elements back to the solar system's early periods of nebular condensation, where the contents of the young solar system were condensing into small subplanetary objects, and those subplanetary objects then formed into planetary objects, what we know today as rocky planets like Earth, Mars, Venus, things like that. So, and from the nature of conglomeration of subplanetary objects into planetary objects, uh, um, and the fact that these siderophilic elements are present within these subplanetary objects, the subsequent bombardment of these rocky planetary objects and planetary bodies, the bombardment of at the end leads to a heightened concentration of these siderophilic elements in the upper crust and upper mantle of said rocky planets like Earth. Platinum group elements, more specifically, are a subfamily, like I said, of siderophilic elements, and they are, they have key characteristics like they are very metallic, they are heavy, they're very good conductors, very corrosion resistant, things of that nature. So they're very useful in many industrial applications, as well as jewelry and fashionable applications. But the fact that they are contained within magmatic ore deposits, um, they are very few and far between as far as particles and concentration, as low as 5 to 15 particles per million in magmatic ore deposits. And oftentimes, these magmatic ore deposits are buried under millions of years of sedimentary material. So, the mining efforts and the extraction and processing efforts to get these platinum group elements is very costly, very dangerous, very hard to do. Hence, why on the end, platinum group elements are fairly rare. They are fairly used in small amounts, and they are expensive to use. They are expensive to purchase. So, how does platinum get all shiny and nice? That's what I want to figure out. How do we get it from its concentration in magmatic ore deposits, in igneous rock deposits, to the shiny lump of metal that we get today. So oftentimes, like I said, these platinum group elements are contained within magmatic ore deposits that are far, far, far underground. And we have to mine underground. We have to blow up the medium, which is the igneous rock medium that the platinum group elements are contained within. We transport that up to the surface. We burn the ever living beep out of it up to 1500 degrees Celsius. And at that temperature, all other unwanted elements are incinerated and burned off. We are left with a hunk of kind of somewhat unrefined platinum group elements. And in many industrial cases, in manufacturing cases, this is good enough for their industrial uses. But a further refining process is required to get to the level of purity that we often see in jewelry and some things like catalytic converters and gold, like in computer circuitry. So, oftentimes, when we want to know the distribution of these stereophilic elements in the earth, we have to go around and we have to dig up rocks and we have to take rock samples, and then we have to study the concentration of the stereophilic elements and the heavy earth elements that we want in these said rock elements. And depending on the differences in concentration in these different rock types, we can make various conclusions regarding the formation of early earth, the formation of the inner layers of the earth, and we can lead to conclusions regarding the characteristics and habits of the early solar system, and specifically the subplanetary bodies in our early solar system. So, for instance, here I have two graphs that I constructed from data that I got from one of my papers. It was a very good paper, but in that paper, they studied the distribution of stereophilic elements in Earth's upper crust and upper mantle, and specifically in basalts and chondrites and igneous formations and various things of that nature. And they did it with many stereophilic elements that were in question. So, for instance, on the graph on the bottom, we can see that the distribution of certain stereophilic elements in basalts and Earth's upper crust vary very much. Things like platinum and gold are very low in concentration, while things like tin and other I think it's astenite is one of them are very high in concentration. And inversely, we can look at the graph to the right and we can see the distribution of stereophilic elements in chondrites, which are one of the oldest rocks on Earth, is directly related to Earth's early formation. So from this, we can figure out characteristics regarding Earth's early formation, and from those conclusions, we can make theories about how Earth formed and what Earth may have been like a gajillion years ago. So, in the middle there, just for to cover my bases, you can see that I've listed the references to each picture, and they're labeled with corresponding numbers. That way, I'm not stealing from anybody. I don't want to steal. I'm not a thief. So, that is the overview on stereophilic elements, how they form, how we get them to be shiny, and how we know where they are, and how we can make conclusions on how they relate to early Earth formation and other conclusions of that nature. Now, how does this relate to my major as a mechanical engineering major and a junior currently? So obviously, like I said earlier, there's a wide range of uses for stereophilic elements. And a lot of those uses happen to fall into my wheelhouse of mechanical engineering, as far as computer circuitry, as far as automotive vehicles, and other things of that nature. So, for instance, let's start out with computer circuitry. There are many gold alloys and platinum alloys in your phone, in your logic board, in your PC, in your MacBook, that underpin the logic board and the circuitry that make your computer be a computer. So, without that gold, without those stereophilic elements in your phone, no more phone, no more Instagram, no more TikTok, boo-hoo. And then I always wondered, why are people stealing catalytic converters? We live in Memphis, you know how it is. The reason is there is a concentration of palladium and platinum in those catalytic converters that aids in turning bad gases from your engine's combustion cycle into good gases uh, like water and carbon dioxide that we can breathe and not die from. And so the natural characteristics of platinum and palladium allow them to perform that catalytic process. And therefore, they are used in cars, and therefore, people steal them because platinum is cool. And then some things about going into the future in electric cars. There is precious metals in that Tesla. Specifically, we can look at cobalt, nickel, lithium, things of that nature that make up the batteries that power these electric vehicles, which are really cool. That's in my wheelhouse. I love automotive engineering. That is my go-to. And so, as we move forward into the electric car generation, electric car revolution, future, whatever you want to call it, these stereophilic elements are going to become more and more useful in powering the vehicles of tomorrow and the day after that. So, what did we learn? We learned a lot of things. I'm talking very fast, but whatever. We learned that precious heavy metals have been used in various applications, from jewelry to manufacturing process to cars to computers. Though we commonly know them as precious heavy metals, stereophilic elements have a unique formation process and harvesting process that makes them very unique and deeper than just precious heavy metals. That's too general, too not specific. Harvesting these metals and these things and stereophilic elements are hard, costly, labor intensive, hard to do. Like I said, that means they're low in concentration. We're not going to have a lot of them, and they cost a lot. Sorry. Though these metals, though the harvesting methods are relatively hard, relatively complex, relatively labor intensive, their applications are endless. Like I said, jewelry to cars to computers to whatever. In the new age of electric cars, the stereophilic elements underpin the foundation of the propulsion system. So they are very key in electric cars. And so the final question remains, what will we do with these stereophilic elements in the future? What will our future look like when we take these stereophilic elements into account? Only time will tell. That's what I'll say. Let's zoom back out. You can see my references in the bottom corner. If you really want to see it, all that mumbo jumbo, you can have at it. That is my time for today. This is my third time recording it. If I had to record it a fourth time, I'm going to be speaking faster and losing more details. It is me. I had fun. See ya on the other side.